I'm Kelsey Allen, a PhD student with Josh Tenenbaum, and I'll be presenting our work on rapid trial and error learning for creative physical reasoning and tool use. Let me first set the scene for you. Imagine you decide to escape this whole coronavirus nonsense and society by taking a spontaneous camping trip to the middle of the woods, but unfortunately, lots of other people had the same idea, and the only leftover camping spot is particularly rocky. Usually, you would have brought a hammer to make sure your tent stakes go into the ground, but in your rush, you forgot it at home. Being a brilliant and creative future PhD student, you don't let this stop you and you start looking around for an alternative hammer. You search around and find a pinecone stick and 2 rocks of different sizes. Which would you choose? Well, probably not the pinecone, since it would break in your hands as soon as you applied force. And probably not the branch, because it doesn't have enough surface area to reliably hit the stake. Between the 2 rocks, you would probably pick the larger rock, as you can get more force onto that tent stake. If your first attempt didn't quite work, which it almost never does, especially in graduate school, you might try a different angle of impact or look for an even larger rock instead of suddenly switching to a pinecone. This kind of rapid trial and error learning requires a really deep physical understanding of your environment and how that relates to the specific task you're trying to solve. This kind of creative physical reasoning is quintessentially human, but humans are not the only species that can achieve such feats. This crow displays similarly awesome behavior in trying to get a seed out of a tube of water that it can't initially reach. The crow realizes that it can drop heavy blocks into the water to make the seed rise. After dropping in 1 heavy block, it checks to see if it can reach the seed. However, after that failure, it immediately realizes it needs to add in at least 1 and perhaps 2 blocks in order to reach the seed. It checks the weight by throwing the block around to make sure it's a heavier one before dropping it in. In Josh Tenenbaum's lab, we were trying to reverse engineer this creative physical problem-solving process. In order to do that, you need to collect lots of human data in order to compare computational models to. Because most traditional tool use tasks require in-person interaction, this has been really difficult to do for the cognitive science community. With that in mind, we built a 2D physics game to collect a large amount of data from both adults and children online. The game is very similar to our camping example. At the top, there's a goal description, and the goal is always to get a red object into a green goal. On the right, you have access to 3 different objects to select from. You can choose any object and then place it somewhere in the scene. Once you place it, physics is turned on, and you get to see the result of your action. Critically, you only get a single action to solve the level, and if it fails, you have to reset and try again. So this is an example of a participant playing one of the levels. They first choose the triangle object and try to hit the ball into the goal directly, but when they see that that doesn't work, they switch to a new strategy, namely trying to catapult the ball directly into the goal. And when that fails, they realize they're on the right track and simply place the object higher to impart more momentum to the ball and get it in. You may not realize it, but in all of these examples, there are actually an infinite number of things we could do, and an infinite number of things we could imagine doing to solve these tasks. Naive approaches to planning, even if you have a perfect model of the world, cannot work in infinite action spaces. So how do people cut down on what they even consider? And how do they use their observations to guide what they imagine in the future? These are the central questions we aim to answer in our first study. We designed a bunch of levels to examine this creative physical reasoning process across a broad range of physical concepts. Some levels require creative thinking about how to move something you cannot hit directly, such as that catapulting level, or others, like Towers B, where the red block cannot be reached. Other levels require creating a support, like Table A, where you must support the falling plank by putting a table leg beneath it so the ball can roll across the top. Furthermore, if you're hip to the current AI craze in image-based end-to-end deep reinforcement learning, we designed 6 adversarial level pairs, such as shafts A and shafts B, where there are minimal changes to the visual scene that result in drastically different strategies being needed to solve the level. This specifically points out that image-based deep reinforcement learning fails to differentiate when only small changes are present, while people take clearly different actions in these cases, and I'll show you some data to support that in just a little bit. People show a wide variety of trial and error learning on this game. On the left, this participant first tries to use an object in order to hit the ball directly, thinking that maybe they could launch it into the goal. However, when this action fails, they reset the level and do a classic thing our participants do, which is to choose exactly the same action again. Of course, it still fails. So now they think a little bit longer about what they might try next, and instead of trying exactly the same action again, they put the block underneath to create a support, but realize that they need the slightly shorter table leg in order for the ball to go into the goal directly. On the right, I'm showing an example of a slightly harder level where a participant needs to hit a red ball into a goal, but it's difficult to hit the red ball directly because it's being blocked. So the first thing they try doesn't even touch the ball, and the second thing they try makes the ball move a little bit, and we might be very optimistic that it's going to go into the goal and really hope that it'll go into the goal, but that unfortunately also fails. They try to get more momentum on the ball by using the heavier block, but realize that they just can't quite hit the ball, even when they try any of the different tools. And then they try something a bit different and realize that the hook can rotate around that platform and hit the ball in an unexpected way. And they fine-tune that strategy to drop it from higher in order to finally get it to work. So people in these two different levels demonstrate at least two kinds of things. They first had structured object-oriented initial attempts, they used trial and error learning to fine-tune their strategies, and then they demonstrated aha moments of insight when they figured out exactly what they needed to do. So how are we going to reverse engineer this process? Well, we are going to propose a computational model to capture the three different observations of human action from that previous slide, namely structured object-oriented initial attempts, action updating based on previous failures, and a simulation process that we imagine informs the kinds of actions participants bother trying in the actual real environment. This results in our sample simulate update model consisting of an object-oriented strategy prior, a noisy simulation engine that lets the agent form very general if imperfect predictions about the effects of their actions, and an update mechanism that can update the agent's beliefs about what they think will work based on the outcomes of both imagined and experienced actions. This is based on problem solving as search, a classic approach from cognitive science, and reinforcement learning. Critically, we're presuming that people update strategies, not models, with the intuition that people already have fairly good models of physics and instead need to learn how to use those models effectively for one particular task. To determine whether this model is a good explanation for human behavior, we ran a large experiment with almost 100 participants on Mechanical Turk. Each participant played 14 levels, consisting of all 8 unmatched levels and 6 randomly selected from the match pairs that I mentioned earlier, and we record their tool choices and placements. As a coarse first look at the data, we can compare how many attempts people take to solve each level, human attempts here on the y-axis, and how many attempts the model took, model attempts here on the x-axis. We can also compare how often people solved a level at all, human accuracy on the y-axis, and how often the model did, model accuracy on the x-axis. In both the case of accuracy and the number of attempts until solution, we see very good correlation across the 20 levels in the game. This suggests that at least at a course level, the model is capturing human behavior pretty well. But those are pretty coarse measures, so let's zoom in a little bit to see whether the model solves levels at the same rate that people do. To look at that, we can plot the cumulative solution rate, or the number of participants who solve the level in X attempts for each level. Across most levels, the human line in black and model line in red are well matched, suggesting that the model solves levels at a similar rate to people. Let's zoom in even more on just a couple of levels and look at the precise placements used by people in the model. We'll look at 3 examples where the human rate and model rate agree quite nicely, and one where they do not. Visualized here are the first and last placements for both humans and our model. Each colored point represents an individual participant, with the color representing the tool they chose and the position being where they put that tool. The model's choices are shown as the blobby background colors. We were really excited to see these results, as the model appears to be capturing the same kind of initial multimodal distribution that humans show across most levels, and converges to a similar set of solutions to people. Take a look at the first attempts in Catapult, for example. Both people and the model try 2 kinds of solutions, hitting the ball directly with the triangle, or catapulting the ball with one of the 3 tools. By the last placement, people in the model have converged successfully to catapulting the ball with the large block. On the other hand, take a look at Falling A, an exception with respect to the rest of our 20 levels, but fascinating because of that case. In Falling A, people are surprisingly bad, much worse than the model. This level is really easy to solve if you put any object underneath the container to tip it over. but people were very biased to put something above the container and therefore took much longer to find a solution. This suggests that people might be using more interesting contextual priors than what we have included so far. As predicted, people's strategies from the very first attempt do differ dramatically based on which match level they played. This implies they must be sensitive to fine-grained changes to the scene, which affect how likely their action will succeed, even without first observing any of the dynamics. To really understand which components of the model are important for predicting human behavior, we can ablate different parts of the model and see how well they fit our human data. There are three components that we could possibly remove: the object-oriented prior, the simulator, and the updating mechanism. We additionally test two alternative models based on current approaches in AI. The first one is a deep image-based model-free reinforcement learning algorithm called the DQN, which was used by Google DeepMind researchers to play Atari video games at human-like levels, as well as a simpler model-based reinforcement learning method where only the model is updated based on world observations. So this would be equivalent to learning the mass or the elasticity or the friction of the different objects in the world based on observations, but not to learning the strategies directly. If we look at how well each of these models correlates with human accuracy across the levels, we can see that in all cases the alternatives are much worse than the full model, with the image-based DQN performing worse than all other structured object-oriented approaches. Indeed, the DQN performs comparably to a method which simply guesses randomly about where to place an object, and certainly does not differentiate between match-level pairs. Here are two levels that illustrate why both the object-oriented prior and the updating mechanism are needed. On the left is the bridge level, which is solved by placing the pink object underneath the two planks. In this case, the problem is just search. People do not generally fine-tune their actions and instead require an aha insight to succeed. Hence, the ablations and alternative methods that use the structured prior, i.e. the full model in red, the parameter tuning model in purple, and the no updating model in orange, perform much better than methods which do not use this structured prior. On the right is the catapult level, which often requires fine-tuning a strategy to drop an object from higher up than you tried initially. In this case, the methods that include updating, i.e. the full model in red, the no prior model in brown, the DQN plus updating model in green, and the no simulation model in yellow, perform much better than those which do not have this updating mechanism, reflecting the importance of learning from previous actions for this particular level. Based on these results, we believe that model-based strategy learning underlies rapid, flexible trial and error learning. However, there are several limitations to the current approach that we are working to address, and some which we have already addressed in papers that are under review. I noted that our object-oriented prior is overly simple, and therefore does not account for some of the levels, like needing to tip over that container in falling A. In exciting ongoing work, we are showing that people can learn these priors from repeated interaction, and that they generalize to very different scenes than those that people were trained on. These priors seem to encapsulate physical concepts like tipping something over or catapulting something, rather than simpler ideas like just placing things above or below objects. Similarly, we have assumed here a very simple continuous physics simulator, but significant cognitive science work has pointed to the importance of events for representing the world. In some ongoing robotics work, we have pushed this line of thinking forwards to reason about more complex tool use based on event representations. Going forwards, we are also extending our game to allow for tool creation, which requires more sophisticated planning and causal reasoning. If you're interested in this work, please don't hesitate to reach out to me. We also have a link to our game, code, and an extended paper at the link below. I look forward to seeing some of you next year and wish you all the best of luck with your interviews. Thank you for listening.